here's another more challenging example, and we want to find the area of the purple shaded region using an iterated integral, and we have to consider this as two separate regions, as this drawing would show. This one has an upper limit of the semicircle and a lower limit of y equals 0. This one has an upper limit of the semicircle and a lower limit, the equation of this line, whatever I want to write, y equals something or other for the equation of that line. So we need a couple things. The equation of the circle, but that's kind of an obvious one there. X squared plus y squared equals 4. Actually, I gave it to you, so duh. But the line's not so obvious, so how do you find the equation of the line that connects the point 0, 2 with the point 1, 0? Well, first find the slope. And the slope of it is negative 2. And the y-intercept is already given at 2, so there it is. Y equals negative 2x plus 2. So, the area of this region is given by the sum of the integrals. It's kind of like the lavender part plus the blue part. Let me see which one I write first. Now I got the blue part. It's the blue part here plus the lavender part here. Here's the blue part. Our bottom limit is this line here, so negative 2x plus 2. The upper limit is this y equals positive square root of 4 minus x squared. And notice our integrand is 1. dy comes first, as you would have expected because of the way I designed this. And then dx next. So, and for the purple region, that's the blue region here, right? The purple region, we have 0 at the bottom, y equals 0, and y equals, again, that upper semicircle. And our x limits, I didn't say anything about the x limits for this one, but 0 to 1 for x here, and then 1 to 2 for x here, because we're starting, the purple region starts at 1 and ends at 2. So, there are many, many computer algebra systems, including mine, that will evaluate this for you like nothing. But the hard part is setting it up. Evaluating it, not much to that. It's really not that hard to do most of the time. Of course, there are some integrals that are really bears, and hopefully you studied a little bit of that in techniques of integration in calculus too, but some are really difficult. But we'll find that here the difficulty is going to be in looking at this region and coming up with this as a solution for finding the area of the region. So the hard part is the human part, as always, not the machine part. So anyway, what we have here, integrating 1, we're just going to get y, right? This integrating with respect to y. So then y would be going from this to this. So that means square root of 4 minus x squared minus negative 2 plus x, or sorry, negative 2x plus 2 dx. And then for this one, again, it's easy to say integral of y dy. Well, y goes from 0 to here, so we just replace that. I could say minus 0 here if it made anyone feel better, dx. So notice this part here plus this part here. This part says from 0 to 1, the semicircle. This says from 1 to 2, the semicircle. So we're really doing the semicircle from 0 to 2. And then plus, notice minus and negative, so plus 2x minus 2 between 0 and 1. So this is really our integral representing the area. And then finally, we got to simplify it as we can. By the way, the radius of this circle is, I'm leaving it blank there, you're supposed to fill it in. 2, right? Yes, it is 2. That's right. Okay, so since the radius of the circle is 2, the area would be 4 pi. However, if we're only integrating between 0 and 2, we only want 1/4 of that circle, and so we'll just say pi for that part. If you insist, you could work this out. If you let x equal sine of theta, you could work out something with arc sine for that eventually. But I think I'm just going to look at it and say, hey, it's a semicircle, and actually it's a quarter circle, and the radius of the quarter circle is 4, so the radius is 2, so therefore pi r squared, so 4 pi for the area of the circle, so 1/4 of 4 pi, or just pi for the semicircle. And integrating this, of course, we get x squared. Integrating this, we get 2x, and that's evaluated between 0 and 1. So put in 1, we get 1 minus 2, and put in 0, we get 0, so the whole area is pi minus 1. That's what this all is. Now, could we have figured that out without all this torture? And the answer is, I hate to say it, but yes.
Yeah!
Yes, we could, because we know this is a semicircle, or sorry, a quarter circle, and this circle has radius 4, so we could have figured out what's the area of that, and that's pi. That's kind of an obvious one. And this is a triangle with base 1 and height 2, so why not just say it's pi minus the area of this triangle, which is 1. So I guess I saved myself a little calculus, but I did want you to see how to set this up as a problem involving an iterated integral.
Woo!
Okay.